influenced by climate and socioeconomic changes.
Thanks for the introduction. Hi, everyone. I'm Chenghao from University of Oklahoma. So we're going to change our topic slightly. So, basically, just a bit background about our research. So, why we're interested in this study. So, as we all know, grids are a critical component of our national or even global energy use. And according to US EIA's survey last year, commercial and residential buildings together account for about almost 40% of US energy consumption. And this number can get even higher in cities where we have denser buildings and also denser distribution of population. And buildings are expected to play an increasingly important role in creating a net zero emission economy by the mid-century, as stated by the U.S. government. And we really need a better understanding of how our future building energy demand will evolve in the near future. Well, things can get even more complicated when we consider there can be a wide range of possible future trajectories, including not only future climate change according to IPCC AR6. So even in the mid-century, we already have a wide range of potential global surface temperature change across different SST or so-called shared social economic pathway scenarios. And associated with all these different SST scenarios, we will also likely see different changes in our urban population. On top of all these uncertainties, we can also have changes in our energy sources for electricity generation. Well, the key question we want to answer in this question is what are the impacts of future changes on building energy demand in US cities in the mid-century? Well, to answer this question, we really need a suitable tool. According to most of the existing studies are mainly at national level, state level, or local zone level. According to their spatial resolution, they are insufficient to capture the city level dynamics. And another common issue facing most of the existing studies is the simplified representation of climate change. Most of the studies are still using temperature or some temperature-related variables like cooling degree day or heating degree day. And some of them are also assuming static population. Well, I should say most of them are assuming static population and or even a static power sector as limited by available data. So basically we don't have such a tool available. So this is why we developed this very sophisticated hybrid bottom-up approach to estimate city level building energy use. So this hybrid bottom-up approach actually integrates physics-based building energy simulation, statistic models, and survey data. So basically, the first step of this approach is to develop this comprehensive hourly urban weather database, or so-called TRUTH, in which we are trying to capture historical and future weather conditions, including extreme events such as heat waves and cold waves. We first used the gut-filled historical hourly weather observations, real analysis data, and a physical solar model to capture historical weather conditions in the past decade. And we also use downscaled bias-corrected multi-model hourly future weather conditions derived from 10 CMIP6 general circulation models or Earth system models. And then we use this, tons of weather data to drive our physics-based building energy modeling using the whole building model simulation engine, the so-called Energy Plus. And we performed in total about over 8 million simulations across the entire states. But one thing I want to mention here is the raw outputs from all these Energy Plus simulations are not a true representation of the diverse characteristics of building stocks among different cities, because we are using the prototype buildings developed by DOE. So fortunately, the DOE has developed so far the most comprehensive and I would say the most accurate end-use load profiles for the entire U.S. building stock. So it is built on the so-called red stock and Comstock models, and it has been extensively calibrated and validated based on public and private data sets across different temporal and spatial scales. So we use their outputs and trained location-specific calibration models to calibrate our raw outputs into more realistic building energy use in different cities. And in addition to that, we also introduced the high-resolution future population dynamics and also the projection of our power sector scenarios into the future to convert our raw site energy consumption into source energy consumption. In this way, we can consider the energy losses due to transmission, generation, and distribution. So let's first take a look at the electricity use. Here we are using the site energy use intensity, which is an indicator quantified by the ratio of final energy consumed in buildings to the total floor area in an urban area. So in this way, we can sort of isolate the impact of climate change from population change. So first of all, I'm only showing two plots of our four scenarios, SST126 and SST585, which sort of bracket the potential future warming. In general, the annual site electricity EUI change on average ranges from 0.1% for SST126 to 1.8% for SST585. And also in most cities, the decreasing trend of space heating demand due to warming can be partly or even completely offset by cooling demand increases. Although on average the change is relatively small, when we look at the specific cities, we see strong spatial variability among cities, even in the same county, such as the Great Lakes and some cities along coastal California. So this is mainly because of the background climate, as well as the diverse, unique building stock characteristics among different cities. So another benefit of our detailed bottom-up approach is we can further analyze the peak energy use. This is especially relevant when we are trying to analyze the resilience of our future energy supply under extreme conditions. So in general, we see a higher increase trend in electricity EUI during the warm season and the hottest day than the annual average. And this is the case across four different SST scenarios. We further define the peak hours as hours with electricity EUI higher than the 95th percentile. In general, the maximum city level increases in the number of peak hours can range from 94% all the way to 170% under different SST scenarios. And especially pay attention to this part, we are seeing considerable increases in coastal cities along California because of both the increasing usage of AC and also the AC adoption rate change in response to future warming. We also further quantify the response of annual site EUI for space conditioning. So this is in general, we have a set of 40 models so that we can derive a linear response of space conditioning to city level future temperature change. In general, for site electricity EUI for cooling, it will increase by 14% for each 1 degree Celsius local warming. For site fossil fuel use, it will range from 9% to 11% for each 1 degree Celsius local warming. We further introduce two different electric power sector futures. One is so-called business as usual, in which we assume there will be no future carbon policies after 2021. The other one is zero carbon scenario, in which we will implement new policies to to eventually achieve net zero by the mid-century. So these two plots show the SST scenarios combined with business as usual electric power sector scenario. And this one is 5A5 combined with zero carbon scenario. Well, across all these scenarios, the building source energy use is always higher. The change is always higher than SST 5A5, followed by 126 and 245. And the lowest one is SST 370, in which we actually see decreasing trend among different cities. I should have a plot here. Anyway, so if you look at this, dependence of changes along with longitude, we see a strong south to north gradient, mainly because of both climate change and power sector decarbonization, as indicated by our decomposition analysis. So take-home message of this study is, well, first one is, we saw a heterogeneous response of city-level building energy use to future changes in the 2050s. This will be highly informative for location-dependent changes for energy saving and energy efficiency among different cities. Second one is, we see stronger changes of energy use at hourly and seasonal scales than annual scale. This also implying that we need to pay attention to this kind of temporal heterogeneity for regional extension of generation capacity and energy storage. The third one I want to mention here is the city level response we quantified, which can be easily used to quantify to convert the cooling effect of, for example, the UHI mitigation effect into the energy saving or energy increase in the future. Last one is, we need to especially cautious about social economic projections when we doing analysis for future energy consumption change. So just a few more presentations this week from my lab, and we're also hiring new PhD students. If you're interested, please scan this QR code and contact me. Thank you.
Thank you, Chenghao. The power of possession of the microphone as the first question, and then I'll go back here. So in the building stock that you modeled, presumably this is a building stock that includes buildings built 10 years ago, 20 years, 30, 50 years ago, to the codes and practices that were in play there. Can you talk about whether your modeling going forward includes characterization of the future building stock? And if not, to what extent do you think the future evolution of building stock will be able to keep pace with the increased warming?
That's a really great question. So one of the assumptions we made for this study is we are keeping constant building stock as present. And this is partially because in the recent survey conducted by EIA, the building constructed after 2010 only account for a very small portion of the entire building stock. But our next step is to introduce the advanced electrification of all buildings in the mid-century, and to see how it will change the landscape of electricity and fossil fuel usage.
Thank you for the talk. I have a question on the details, I guess. So you said in this model we considered the air pollution adoption rate changes under SSD and SSD scenarios. I was wondering how that is modeled, and if you use like a empirical model or was it based on observation?
Yeah, it's actually an empirical model, actually an improved version of Dr. Sila's model. So we actually divide the response functions for different CMIP6 models according to their cooling degree and heating degree phase. Yep.
Is it also based on the income increase in these places in different cities?
You mean socioeconomic changes?
Yeah.
Like status? Nope. So only temperature indicator. Thank you.
Very nice talk. I have a quick question. So, do you have a rough idea how to translate your building energy consumption data to the, let's say, nitrogen heating release, so that we can use in the living space?
This is what we are working on.
Awesome. Thank you so much.